The next speaker is Julian Nadeau. He is struggling the monolith and legacy Ruby application. I feel same. So how I can understand how you're struggling. So the title is Busting Performance Bottlenecks, Improving Boot Time by 60%.
Hello, my name is Julian Nadeau. I'm a production engineer at Shopify. You can see my GitHub and Twitter handle at the bottom. It's Jules2689. And first I'd like to talk a little bit about what Shopify is. So Shopify is a Canadian company that was founded because of snowboards. So in about 2004, our CEO and founder, Lookup, wanted to sell snowboards online. Unfortunately, everything was bad. The software at the time wasn't very good, and it would cost about $100,000 just to get a payment gateway started. So Toby used Ruby, particularly Ruby on Rails. I think we started on version 0.18 to create the Shopify application. Today, Shopify powers over 500,000 merchants around the world, with lots of merchants actually in Japan. We have our Tokyo office, which was started recently. And we now boast a multi-million line code base running on Rails 5.1. So we've made sure to stay up to date. So we have about 1,000 engineers working at Shopify. So this topic is pretty dear to us because it saves us a lot of time and money. So first, what is application boot time? We're going to start the talk with that. We're going to talk a little bit about why it matters. We're going to talk a little bit about why it impacts you and what it impacts your organization. And we're going to talk a little bit about how it impacted our application at Shopify. We're going to follow that by talking a little bit about areas of impact and how we mitigated those, particularly the BootSnap gem. I'm sure some of you have heard it in the other presentations. BootSnap is a gem that we recently released. And I also did some work in Bundler 115 around performance. The bulk of this presentation, however, isn't going to be about what application boot time is or what we did. That work is freely available in open source. But what I'm going to do is I'm going to talk a little bit about the simple but powerful techniques that we used to actually find the inefficiencies in your own code. Hopefully you can go back and fix the problems in your own code base. So I've also prepared a website and a GitHub repo with a lot of this demo information. Feel free to reference that throughout the presentation or afterwards. So application boot time. What is it? So very simply, it is just the time that it takes for your application to start after the start command has been issued. So for example, if I run bin Rails server in a Rails application, it takes 8 seconds for the application to fully initialize, which means that 8 seconds is your boot time. Now, that might not seem like too much, but if you consider that this is the boot time for every time you run tests, and I'm sure most of us, write tests, so, you're running that, maybe 10, 20, 30, 40, 50, maybe more a day, that time starts adding up. Every time you run bin Rails server, bin Rails test, bin rake test, bin rake run, whatever your start commands are, this is the impact that you have on your application. But why does it matter? Well, a developer's experience with your application depends on their perception of how easy it is to work with it. We have our products. For Shopify, our product is an e-commerce platform, a commerce platform. But the developer experience is also our product. With 1,000 engineers, I am part of a team in our production engineering department that runs and maintains the product that is our developer experience, which means that we need to maintain and give them the same experience that we would give our own merchants. And application boot time causes that wait time to increase. It causes that easiness to become hard, and the perception becomes more negative. These negative interactions will start to impede productivity. It'll start to get people to feel bad about your application, and it'll start making them start context switch. In the end, you'll end up with lost trust of your developers, and lost time, which, time equals money, means you lose money. So in Shopify, this culminated to a boot time in tests of 25 seconds or more, as well as with our server. Times this by the number of developers we have, about 1,000, and how many times they run it a day. We were, hemorrhaging money, tens of thousands of dollars, potentially every day. And, I'm sure you've seen various comics online that joke about, somebody going and poking your developer or a developer at all, and they lose 30 minutes of time because they have to go back into context. Now imagine your own application does that. Imagine that's the impact your own application has. And this is why we started working on boot time. So with that in mind, I'm going to talk a little bit about the areas of impact that we found within our own application before diving into how you can detect these inefficiencies yourself. So the first bit is compiling, serialization, and lookup. So compiling. Compiling code in Ruby is done dynamically, as you all know. However, it is a concern within boot time performance. As your application grows in size, you have more and more code to compile, particularly with requires at the top of each file. What this means is you have an increased amount of time relative to the application size. Luckily, in Ruby 2.3, we had a few instruction sequence methods added, and we'll talk a little bit more about how we use those later. The next is serialization. In our case, we use YAML. This is for our test fixtures, this is for configurations, this is for bug snag for our exception tracking, this is for persistent data, this is for a high number of things. Unfortunately, it was causing a multi-second serialization phase within our application's boot. So we learn a methodology by compiling and serializing the content of YAML files using Ruby's Marshall and the message back gem. I'll talk a little bit more about that in a few moments. Next is actually constant lookup. I think there was a little bit of talk about the load path recently at this conference. However, what you might not know is that it's actually really expensive to look up a constant. You have a potential of O(n) squared time because you have to go through the entire path each time for each of the things that you require. And as you add more things to your application, as your application increases in size, the load path increases relative to the size of the application. And this can actually have a detrimental impact on the performance of your application. But luckily, we can also cache this. Once we know the layout of your application, we can cache the first iteration and change it from an O(n) squared time to an O(n) cache hit or miss. I'll talk a little bit more about this later. And by later, I mean now. So we're going to start by talking a little bit about how caching works within BootSnap, because there's two paths. So first, does everyone kind of know what the BootSnap gem is? Anyone not know? Okay. So since everyone kind of knows a little bit about BootSnap, we'll start by talking about the basic caching protocol that we use. So there's a stability check. And what we do is we check whether or not we can consider a file or a constant stable or volatile, which means will it change or will it not? We consider both gems and Ruby installs to be stable, which means that we assume that you're not going to go and modify the gem within your file system. You're not going to go modify Ruby code within your file system. And this holds true for the majority of applications. For the Ruby core committers, this might not work, since they'd be changing Ruby a lot. However, everything else is considered volatile. I'm not going to go into the specific details of each of these. However, once we consider your file stable, so it's the gem or it's a Ruby install, we're going to cache this directly into a cache folder using Ruby ISEC compile instruction sequence. And we're going to do the same actually for the other files, but there's an extra cache key added on. So in the stable cache, basically we just cache it for forever, whereas in the volatile cache, we cache it for 30 seconds. This allows us to cache it for the duration of your boot. We assume your application. and allows us to fully cache the application after the first iteration. So I mentioned before that we had issues with compilation. So in this case, we are compiling bytecode. So I mentioned the instruction sequence. In Ruby 1.9, as one of the previous talks mentioned, Ruby translated Ruby source into an internal bytecode format, which is then executed by the VM. And this was actually a big change. It made it faster, it made things better, and it allowed us to hook into this point since Ruby 2.3, where an API was exposed. So in Ruby 2.3, the Ruby VM instruction sequence load ISEC was introduced, which allows us to bypass a pretty expensive compilation step that happens every time you load a file. So in Ruby, what will happen is you're going to load a file. Maybe it's just a hello world file, but that does get compiled. But if you require that file multiple times, or you reference it multiple times, each time you're going to compile again and again and again. What we do with BootSnap is we cache it after the first time, and it will never be compiled again. We'll use the very fast load ISEC and compile from binary, the entire instruction sequence, starter pack basically, and we're going to use that instead. This increases time by a lot. One interesting thing to note is I found out from a previous presentation that these methods were added, and Koichi actually specifically said, we do not want people using this. I do apologize to Koichi, but this has been a default gem in Rails since 5.06, I think, so there's no going back now. Good luck. Next is actually the serialization and configuration of test pictures and other configs. So we notice that YAML.load file, which is often what is used, is actually super slow. Even when you use a really fast, C extension for this, it's still really, really slow. And there was no way around that. Or so we thought, until we realized that message pack, or marshalling, is very, very fast in comparison to YAML serialization. And the reason YAML is slow is because it's a very dynamic language itself, so you can start merging things, including things, and importing things. And that becomes, that's where a lot of the slowness comes from. So by caching this as well with the same volatility checks, we can reduce boot time. Next is we override kernel require and load to fix file and constant lookup. So we're not going to go over too much of this. It's all listed here, but basically within the Ruby language itself and within Rails, we will override all require methods, all load methods, and try and use the cache first. So you might notice that these kind of work together. Before you had a file constant lookup that was really, really slow, maybe ON squared time, and then you had a really expensive compile phase. So every time you tried to do something, you were hit by this double whammy of super slow, non-performant serialization, compilation, lookup. But with BootSnap, we get rid of all of that. If you look at the file system calls, instead of like opening a file, closing it, there was like, I think there was something like 30, 40, 50,000 lines of like system calls for a lot of this stuff. It's now just like open, close, done. It's but by caching this constant lookup, we can get to a file immediately. We have that file that we just looked up, we already have compiled and cached, so we just saved a lot of time there. And this is the BootSnap library. So you can install it by adding it to your bundle gem file. Make sure to have require false. We don't want to require this before bundler itself. It causes a few issues. And right after bundler setup, put in require BootSnap setup, and you get a significant increase in your own boot time. So Discourse, a common forum platform in Rails, saw a reduction of 50% from 6 to 3 seconds in their own boot time. One of our smaller internal apps went from 3.6 seconds to 1.8 seconds. And the core Shopify platform, a rather large monolithic multi-million line code base, boots about 75% faster, going from 25 seconds to 6.5 seconds. This is a pretty big impact, and we've seen this in a lot of other applications. While talking in the bundler Slack, I heard from a number of other people that they were putting it on their projects that had 45, 60, 90-second boot times, and they were seeing some pretty good increases as well. So this is available open source. You're welcome to use it. If you have any questions, let me know, and we can go over a little bit more in depth if you'd like. The next area of impact was bundler. So bundler is this tool that pretty much all Ruby developers use. It gets gems, it gets all the dependencies that you need. But what was rather surprising for us is that it took about 1 second of boot time, which doesn't seem like a lot, but when we're trying to get down to a 6-second boot time and we're at 8 seconds, that's a pretty big jump. So we started looking into this and realized that there was a number of optimizations that were missing, and I want to go a little bit into those. This is all released in Bundler 1.15. The blog post is on the Bundler blog, and this cut down the boot time for that 1 second by about 60%. So after it was done, for us, it took about 300 milliseconds rather than a second, and we saw similar performance increases for all other applications as well. So if you haven't already upgraded, Bundler 1.15 is very stable. We released all 3 releases to the 1,000 engineers we had at Shopify, so it was pretty easy release for everybody else. And we are going to continue to do that upgrade. You might have heard a little bit earlier with Colby that Bundler 2 is coming out. So, get on Bundler 1.15 as soon as you can. It'll make your lives easier. But bundler. So one of the issues that we had was gem specification validation. You might not know, but Git gems aren't a real thing. They're kind of like fake gems. And I say this because there's no native code within Ruby gems to support Git gems. And you'll find this out when you use gem specs. So what actually happens with Git gems is Bundler will clone the repo. So let's say you're using Shopify's Active Merchant gem, which is open source, and you decide to use it from GitHub. What Bundler will do is it will clone it into a Bundler directory, compile it, build the gem, and then use that gem from a path. So internally, Bundler actually considers Git gems a path-based gem. But what this means is that these gems could not be valid. So when you download them, the gem spec might not work. So every time we were validating that the gem spec was actually correct. But this is really slow, and if you only do this on the first time, you pretty much guarantee that it's going to be valid without doing it every single time. So I guess the first lesson we learned here was avoid all work as much as possible. Try to be lazy. Next was gem file serialization. So gem files have a lot of dependencies, and those dependencies were stored in an array. We then tried to do a lookup on that array based on name, which was doing a total cost of O(n) squared because we were looking up n dependencies at a cost of O(n) time, which is super slow. But what we could do is during that serialization, we could change it to a hash to give us a total of O(n) time with O(n) cost each dependency. This is a Gantt chart that I did for the method here. I'm not sure if you can properly see it. I'll see if I can zoom in. Guess not. But you can see that the bulk of the time here, about 200 milliseconds, is run because of a dependency select and just a comparison using name. And this took 200 milliseconds. So we could easily tell that this is where most of the work was happening. And if we cut that down to using a hash, we save about 200 milliseconds, which you can actually see in this chart here. This is the exact same Gantt chart for the exact same method, but you can see that, where is it? This line here is the exact same line as the one we saw before. So you're able to validate your work because we know that the time that was taken was a lot less. So we went from about 250 milliseconds for this method to about 26 milliseconds for this method. Once we went to that, you could see that about half the time was taken up by this line here, which is the converging of dependencies. So what we were doing here is we were extracting names from requirements from the dependencies, and this was done twice for a total of O(n) cost, but we're doing it 2 times, and we compared things as set objects. This was really slow, so instead of doing an O(n) comparison using requirements and names, What we did is we used the hash from before and changed it to a total O(n) time and cut that time in half, which you can see right here again. It's cut down by one of these lines here, probably this one here. Yeah. So by doing that, we saved another 13 milliseconds, taking that total time of that method from 250 milliseconds to about 14. This might not seem like a lot, but oftentimes we found within boot time performance, you're looking at about 200 to 300 milliseconds per method, and that was evident here. So that was some of the areas that we found. BootSnap was a significant benefit for us, and allowing it to be used across all Rails and Ruby applications was super helpful. Doing the work on Bundler was also really great. They were a super open community. They were really great to work with, and really appreciative of the performance work. Since this time, we've continued to do performance work on Bundler and on BootSnap, and I'd like to talk a little bit more now about how we went about finding those. So I tweeted a little while ago about this timing helper. This timing helper is basic. At the top here, in this line, we get clock time. I wanted to be fancy and decided not to use time.now. This makes me look more intelligent. But basically all this is doing is we get time.now at the top. We yield a block, capturing the return. We then output the current time after we yielded minus the last time, which will give us the delta or the difference in time. So it tells us how long that block took to run. This might seem really easy and really dumb, but it's actually super powerful. So you can see right here. In this example, I just wrapped it a sleep 1 in here, and you can see that we took about 1 and like 0.6 of a millisecond to actually run. And that's pretty much how that works. And here's an example actually with Bundler. On the left side here, right here, we have setup, and on each one of these lines, I didn't know what was actually being slow. I knew that this was slow. So this is the main entry point for Bundler setup, which I was just talked about being about 1 second. So I knew that one of these lines, or part of one of these lines, was really slow. So using this timing helper, I can go over here, and you can see that we have definition. I split up here, so we capture definition. We see how long that takes to run. We then validate runtime separately. We then put this print major deprecations. We get groups, so I grabbed this groups here. I grabbed load here, got those up here. This is the same functionality, except each one of these has a time helper wrapping around it, which outputs how long each one of those blocks takes, which allows me to build this. This doesn't, this seems pretty simple for all that work, but it's actually, it's a Gantt chart. If you don't know what a Gantt chart is, it's just a simple chart with time on the bottom and bars across. And what this shows us, based on the labels that we had that initialized, took about 100 milliseconds. These took about nothing. But the actual load.setup, that's where the majority of the time was. So we can start diving into that a little bit more. So to continue this, I don't want to continue with just some slides. So I have a bit of demo code. It's pretty basic, but it's available online with my GitHub repo. So you can see the timing helper I have over here. Pretty basic, and I have a file here with some time blocks. So if I run this, you'll see some pretty basic output. You'll see this block up here, where we just simply output to the terminal, takes about 3.6 to the power of times 10 to the -5 seconds to run. So we don't really care about that. I think that's seconds. You'll see that this time here, where we're doing a while loop, while I is less than 30, sleep 1, you'll see that that took about 3 seconds, as you would expect, since sleep 1 times 30, but 3 seconds. And then you'll see all of these method outputs down here. And you get all method outputs despite only having the one, because we have a recursive call, or a while loop or a for loop, and you wanted to see how long the internal takes. This isn't very helpful. So this particular helper helps until you have recursion or a loop, and then it kind of falls apart because this is unreadable. I mean, you can look through and judge. Like, it takes about a second, but it's not that helpful. What's also interesting to note, though, is it's not that helpful because it's kind of like aggregating time on top of each other, because this calls the top one, but like this call has all of those in it, and this call has all of those in it, so it becomes not as useful. So instead, what we do, what I have here is an aggregate function. So it uses a global variable and an @exit loop, and it's pretty much the same call. You'll see the clock.getTime. You'll see the ensure. You'll see the minus t. And what we do instead, though, is we count the number of calls that happens. And then at the end, we take it and output it in a table of how long each one of those blocks took, how many times that block was called, and the label, of course. So you'll see from this exact same example, we have the same 3 little snippets of code. This is going to be the exact same as the basic from before. So these will be, the first 2 will be pretty much the same. Whereas the last one here is what's going to change. So if I run this, you see pretty similar output, except everything's at a table in the end. And you'll see that those 22 calls that we got before are aggregated to show us a total time of 23 seconds, rather than 22 independent calls, which is pretty great in comparison to having just a blob of text. This is great, but you can go a little bit further. If we take a look at the presentation that I had, you'll see these Gantt charts. I think there's a few more, some Gantt charts here and here. I found these actually the most beneficial tool that I had. And the reason I found these beneficial is because it makes everything really visual, and I could start making flowcharts actually of Gantt charts, which I'll show an example of in a minute. So what I have here is a pretty basic function. This is pretty similar to the aggregation of time, but instead what we're doing is we are grouping some stuff together, getting lines. It gets a little bit more complicated, but what it does is it pulls each line, so you can wrap a function within a Gantt chart block, and each line will be traced. And that way you can find out how long each line takes without doing any extra work. I'm going to put this in just to help understand. But if I run this exact same thing with these 2 methods here, you'll kind of see what I mean. And so the first one here just recursively calls itself. The second, and like it's going to be about equal, because it's not going to take too much time. Each line will take about the same. Whereas in this one here, you'll expect that this line here takes more time than the others. And then this time here will actually take even more time, because it's going to include all of its nested recursive calls. And what I've done is I have a gem called chart helpers that I pushed up to Ruby gems yesterday. I made this like months ago. I only just pushed up to Ruby gems though. And you'll see the output from those 2 method calls. And you'll see that I output this kind of weird syntax. This is supposed to be a human readable syntax, so that you can see, so you can write it yourself, or you can auto-generate it pretty easily from a computer. And you'll see that these 2 files here, so this is the first one with my method. you'll see each line takes about the same amount of time, about 1/3 of the time. And you'll see that this one here is totally paled in comparison to the others because the sleep takes a long time. And you're able to use this in a more production situation by going back to something like this. Whereas I trace each of these individually with a time step, and then I manually wrote this out. With the Gantt chart, you can auto-generate something that will generate this for you, which means that you can just save a lot of that time. So using those timing helpers, these Gantt charts, you can start making flow charts like this. So this is for that same method that I showed before, the load setup. I started diving down deeper into that. And from here, you can kind of see that it took about 663 milliseconds. Setup took 630 milliseconds. We switched over to the runtime file. Request the specs took this much. And you can see I started breaking it down. I cut it off because this flowchart got really long. But I was able to start seeing where the time was happening, and I could focus time on that instead. This is an example of where I ended up going with this. So I took over an entire wall in my office. And you can see the flowchart that I just showed in full form is printed out right here. I then jump into Gantt charts, and I start seeing, you see like this line took a long time, and then I go down to this. So I dove into that method, and I did a Gantt chart within that method to get this line, and I saw that there's one specific line within that method that took a long time, and I kept jumping down, breaking things up. So you have this time here, goes over here, this time here, goes over here, and I started keeping track of notes. Like, you know, I can't do anything more here. This just says dead end, so like I couldn't improve it without a significant refactor. So you can dive deeper and deeper into that. And now those are a few of the methodologies that I used to find the bundler inefficiencies. Those are some of the methods that we used within BootSnap as well to start tracing down, oh, compile takes a long time, oh, serialization takes a long time. You know, it's just really simple time output. You know, I wanted to do this talk to talk a little bit about BootSnap, encourage people to work with bundler, but also to encourage people to look at the boot time of their own application. If we can work on this as a community, we can start identifying those pitfalls before they happen, like not writing your dependencies in an array, using a hash, just basic stuff like that. It's actually really easy to do, and I encourage everybody to take a look on their own app. Like I said, I have the chart helpers gem available. You can use that to create your own Gantt charts. And you can use the timing helpers that I have on the website that I mentioned at the very beginning of this presentation. You can use those there. So at Shopify, we saw over a 60% reduction. You can do this too. BootSnap is available at github.com/shopify/BootSnap. Bundler is available at github.com/bundler/bundler. And there's lots of other open source projects that you can work on, like Ruby gems, that impact the entire Ruby community as a whole. Please help out with these open source projects. It depends on contributors like you. And, thank you, and arigato.
So, do you have any question?
Is stable cache invalidated after bundler update?
Invalidate after bundler update. Yeah, I think it's based off of mtime as well. So we like it's stable as long as it doesn't change, but we do some detection to make sure that it doesn't change. That being said, actually thinking about it a little bit more, when you do a bundler update, it's going to install the same gem but in a different version directory. So there's no cache yet for that directory.
So the cache key includes the version of gem?
Yeah, so I can the cache key includes the path of the file that you're requesting. So since it's going to be in a different path, like we don't actually specifically just cache all gems. As we come across it, we cache individual files within a gem because you might not use all files, so we don't need to cache it all. So we cache individual files, and so the path is used.
So if there are any case that requires to invalidate cache manually,
Yeah, so I mean, it's just stored into a directory that you can specify, or otherwise I think we store it in a temporary directory by default, but you can specify the directory, and wherever it ends up being stored, you can just delete that directory and it'll be recreated within your cache.
okay, thank you.
You're welcome.
So with BootSnap, is there any disadvantage of using it? Is there any time you would not want to put it in your application?
I mean, I can't think of one myself. I mean, it does add an extra layer of complexity, so there's always that to take into consideration. But I mean, given that Shopify is probably one of the larger Ruby applications in the world, and we use it for everything, I don't see. I mean, of course, like other people use Ruby in different ways, so I'm sure there's probably some case I'm not thinking of, but I can't think of one right now.
Okay. And you also talked about the advantages it provides within the development environment. Are you also using it in a production environment?
The last I checked, we're using parts of it in production. It does increase the boot time. So for Shopify, we care a lot about deploy time. So when we boot the application after deploy, we want that to be as fast as possible. So we do use it in that case.
Okay, thank you.
You're welcome.
About 5 minutes left, so do you have any question?
Have you talked to any folks well, obviously you've talked to the bundler folks, but have you talked about ways that you might be able to integrate BootSnap more broadly into non-Rails parts of the open source ecosystem? Rails obviously as well, and
Yeah,
that's a big
so
deal.
Rails was really easy because, well, we use it a lot. At Shopify, we employ at least 2 core contributors to Rails, so we have a pretty good access to that. We didn't try to push it into Rails, actually. DHH contacted us and asked to put it in Rails. So I think in that case, if there's other communities that want to start using it, we have no issue spending the time to help them get it integrated into their environments. Just give us a shout out, tag me or at Burke, B-U-R-K-E, on the BootSnap repo, and we can help you get that set up, because we'd love to see it obviously in all areas. And I guess to preempt the question, we don't want to put it in Ruby because it's fairly opinionated on how it does things, and we don't think it's a proper fit for the Ruby core right now. So thank you.
Thank you. Wonderful talk.
Thanks.
It will be the last question.
Hi, nice talk.
Thank you.
I wanted to ask, when do you think that you'll be done in a realistic manner in terms of performance optimization? What's your goal in a way that's realistic?
So for Shopify, obviously it's never done. Just like any other application, the work is always going to be there. So instead we try to set realistic goals that we try to maintain. We understand that people are going to introduce new things that are going to make things slower, faster, different. So as long as we maintain a baseline, and for the Shopify core application specifically, I think we set that at about 8 seconds as our acceptable bandwidth, or I guess boot time. And I mean, I encourage everybody to do the same. It's just like set a realistic expectation, start tracking it with metrics, whether you use Sentry or Datadog, your own thing, whatever tracking or metric system that you use, start tracking those times, start tracking all this information, and you can, so that way you can be like, oh, it's now 10 seconds on average, let's go and work on that again. Just because it's never done, you can only put it on a shelf for a little while before you have to come back and poke it again.
Thank you.
You're welcome. Arigatou
Okay.
gozaimasu.